Okay, so good evening everyone. My name is Avik Mukhopadhyay and I am one of the TAs for this course on digital signal processing. Today we are going to discuss some sample problems in this live session covering the contents of week 10. So if you recall, in week 10 we started with the notion of linear phase, systems with linear phase, and the condition for linear phase was actually derived. So there were two cases. The first one is the trivial case where we have the impulse response to be 0, which is numerically fine but it doesn't make any sense practically. And then we looked at the non-trivial solution for linear phase, and we derived the condition for that, and we categorized the linear phase FIR filters into 4 types, namely type 1, type 2, type 3 and type 4. And we actually formed a table, and we saw their characteristics with regards to the symmetry of the impulse response, the length of the filter, the group delay, whether it's an integer or a fraction, and etc. And then we saw the constraint zeros of linear phase FIR filters. So we actually visualized the pole zero plot for each of the 4 types of filters, and then we drew some implications for them, such as which one is suitable for designing high pass filter, which is not suitable for designing high pass filter, or not suitable for designing low pass filter, and stuff like that. And then we saw the relationship between the zeros of linear phase FIR filters, and finally we also derived the explicit formula for the frequency response function for these 4 types of linear phase FIR filters. So let's start with our today's session. Okay, so I hope question number 1 is visible. So this is we are starting with a easy question. So in this question we are given an LTI system with a frequency response capital H of omega, and remember this notation, capital H of omega, it implies the same thing as capital H of e power j omega, which is the more common notation that we have used so far actually. So H of omega, capital H of omega, is same as capital H of e power j omega. In other words, it's basically the discrete time Fourier transform of small h of n. So this LTI system has the following frequency response, small h of n, which takes the value 3 at n equals to 7. It is minus 2 at n equals to 8, and it is 0 otherwise. In part A, we need to find the frequency omega at which the magnitude response, that is mod of capital H of omega, reaches the maximum value. So at what frequency does the magnitude response become maximum? That is the first part. And then once we are done with the part A, in part B we need to find the maximum magnitude gain actually. What is that maximum value of the magnitude response? And in part C we need to check if this system is a linear phase system or not, and we have to justify and explain our answer. So I hope the question is clear to you. So let me just note it down here. we are in week 10. Okay, good. So we are looking at question number 1. So the impulse response is given as follows. So h of n is 3 when n is equal to 7. It is equal to -2 when n equals to 8, and it is 0 elsewhere. And we are looking at part A. So now see, in part A we need to find the frequency at which the magnitude response becomes maximum. Okay, so okay, fine. Right. So yeah, so in order to actually find the magnitude response, we need to first find the frequency response itself, that is capital H of omega. So how do we find that? We just simply take the TTFT of h of n. So h of capital H of omega, and remember, like I said, this capital H of omega is the same as capital H of e power j omega. Here we are just using a slightly modified notation, that's it. So this is given by the TTFT formula, which is this. Okay, and now there are only two non-zero samples, right, at n equals to 7 and n equals to 8. So only those two indices, those two values of n will contribute to this summation. So we just first put n equals to 7 and we get this, and the second term would be this. Okay, so what do we get? This is h of 7 is 3. This is 3 times e power minus 7j omega plus, actually h of 8 is -2, so there will be a minus sign. Okay, so it's minus 2 e power minus 8 j omega. Alright, and let's actually separate out the real parts and imaginary parts, because that will be helpful for us to find its magnitude, because we need to find the maximum value of the magnitude and also the frequency at which the magnitude becomes maximum. So let's do that. So again, we just use e power j theta equals cos theta plus j sin theta, that standard formula, and we can write this as 3 times cos 7 omega minus j sin 7 omega. This is cos 8 omega minus j sin 8 omega, and let's pair up the real parts together. So we have 3 cos 7 omega minus 2 cos 8 omega plus, now the imaginary part, 2 sin 8 omega minus 3 sine 7 omega. Fine. Okay. Now what about the magnitude? Mod of capital H of omega. So we just take its magnitude, so it's square root of real part square plus the imaginary part square. So we have this. So if I remember correctly, this kind of a question was, I think, present in one of the previous assignments. I think week 7, 8 maybe. So, and one of the students had asked me a doubt on how to solve these kind of problems. I think it was also related to finding the maximum value of the magnitude response. So this is kind of a sample problem that actually follows the same process actually. So anyways, so what do we have? So this actually gives us 9 plus 4, because you have 3 cos 7 omega, and then you have 3 sine 7 omega, right? So though they become squared and become 9 cos square 7 omega and 9 sine square 7 omega. If we add them together, it just gives the coefficient, which is simply 9. Okay. Similarly, we have a 4, and now the other term will be minus 12. So in the first, if we just expand the first squared term, so it's like a square plus b square minus 2ab. So this is the minus 2ab term. So it will be minus 12 cos 7 omega cos 8 omega, right? So taking 12 common, we have this. Okay, and similarly for the other expansion, we get the sine terms. Okay. Okay, and now what is this? So 9 plus 4 is 13, and minus 12 times, if you see, this is cos a cos b plus sin a sin b, which is nothing but cos a minus b, right? So this is simply cos of omega. So that's it. So this is the magnitude of the frequency response, right? And so for what value of omega, what frequency does this magnitude becomes maximum? So it is clearly like we need to maximize this overall expression here, 13 minus 12 cos omega. We need to maximize this. Okay, so in order to maximize this, see the second term, that is 12 cos omega, that is subtracted. Okay, that is subtracted from 13, so it has a negative sign in front of it. So if the overall expression has to be maximized, this term which is subtracted, that is 12 cos omega, that has to be minimized, right? Okay, so basically 12 cos omega should be minimum, which means cos omega should be minimum. And when is the value of cos omega minimum? The minimum value of cos omega is -1, that's for sure. And in the discrete time, as you know, the limits for omega is from -pi to pi, so, or from 0 to 2 pi, whichever you take. So when does cos omega becomes the minimum? That is, cos omega is -1, the minimum value. It attains the minimum value at omega equals to pi, right? So that's the required frequency. Of course, it's also at -pi, but let's take the positive frequency. So that's it. So oops, okay, so the magnitude is maximum when cos omega is minimum, that is when cos omega equals to -1. Okay, and that happens at, that is at omega equals to pi, and the unit is radians per second. Okay, so that's it. So this is the answer. So omega equals to pi radians per second is the answer. At this frequency, the magnitude is maximum. And now let's move to part B. So in part B, if you see, you need to find that maximum value of the magnitude. See, maximum magnitude gain, that's it. So you just evaluate this magnitude response at omega equals to pi, basically. Okay, that's it. So this maximum value of this, right? Yes. So yeah, recording is fine. So this is basically at the magnitude at omega equals to pi. That's it. So it's under root 13 plus 12, right? Because cos pi is -1, so we already have a negative sign, so overall it becomes plus. So it's square root 25 and it's 5. So the maximum magnitude gain is equal to 5. Okay, now let's come to part C. Yeah, so far it was just simple taking the magnitude and just maximizing it. So now in part C, actually we need to utilize the concept of linear phase. We need to check if this is a linear phase system or not. And so how do we actually check if it's a linear phase system or not? So for that we should be aware of the condition for linear phase, right? So what is the condition for linear phase? So if you recall, just a second. Yeah, so anyway, so sorry for the interruption, let's continue. So yeah, what's the condition for linear phase? So the condition on the impulse response for a linear phase filter is h of n should be equal to plus minus h of capital N minus 1 minus small n. Okay, this is the condition. So it can either have plus sign or minus sign, anything is fine. So if you recall, we actually had the plus sign for the type 1 and type 2 filters which have the even symmetry, that's why we had plus sign. And the negative sign, of course, it's for the type 3 and type 4 filters which actually have the odd symmetry, that's why the negative sign is there. And here capital N is the length of the filter, right? So if you go back to the question, so the given impulse response is it's just basically two non-zero samples at n equals to 7 and n equals to 8. It is 0 at all other indices. So of course its length is 2, right? So only at n equals to 7 and n equals to 8 we have this non-zero values. So here length, which is capital N, is 2, right? So pictorially it will look something like this. So at n equals to 7 we had the value 3, so this is h of n, and this is n equals to 7, and at n equals to 8 we had minus 2, so it's somewhat like this. So this is n equals to, so this is at n equals to 8, and this amplitude is minus 2, and rest all the samples are 0. Okay, it continues 0, 0, 0, and it continues, and so on. This is n. Okay, now if you recall the types of the filters, basically so for the type 1, type 2, type 3 and type 4 linear phase FIR filters, they all had some kind of symmetry in the impulse response, right? And either they were of even length or odd length, that's fine, but at least, so for the type 1 we have even symmetry and odd length. Okay, similarly for type 2 we had even symmetry and even length. For type 3 we had odd symmetry and odd length, and finally for type 4 we had odd symmetry and even length. So at least they have either an even symmetry or an odd symmetry. But if you see this impulse response, if you look at this diagram, does this impulse response has any kind of symmetry? Does it have an even symmetry or an odd symmetry? The answer is clearly no, right? There is no symmetry. So you can directly say that it doesn't have a symmetry, so it doesn't belong to the class of linear phase FIR filters. So it's definitely not a linear phase system. So this actually belongs to neither of the types. One, two, three, or 4, because there is no symmetry. Right. So this you can directly conclude from the diagram, the sketch of the impulse response itself. But if you still the standard way is to actually check for this condition, that is, which I wrote here, h of n equals to plus minus h of cap n minus 1 minus n. You check if this condition is numerically satisfied or not. So let's just do that. So here basically we need to check this condition is true for, if this condition is true for basically n equals to 7 and n equals to 8, right? So let's do that. So again I'm just writing the condition here. This is what we need to check for linear phase. So first we are checking for n equals to 7. Okay, so if we put and by the way, like I wrote in the previous page, so here the length capital N is 2, right? So if you put 2 here, it becomes 2 minus 1 minus n, which is 1 minus n, right? So this we need to check. So for n equals to 7, if you substitute n equals to 7 in this equation, you have basically what's the LHS? So the LHS is h of 7, and h of 7 is given as 3, right? And what about the RHS? At n equals to 7, the RHS is 1 h of 1 minus 7, which is h of minus 6. And this plus minus sign, it doesn't matter. So what is h of minus 6? So it's 0, right? Because it's only non-zero for n equals to 7 and 8, and rest everywhere is 0. So this plus minus sign really doesn't matter here, it's simply 0. So clearly LHS is not equals to RHS. So LHS is not equals to RHS, and therefore this is not a linear phase system. So we have looked at a simple example on how to check systems with linear phase. Okay, so hopefully it's pretty straightforward and clear. And actually, if you also want to verify it algebraically, So let's do that. Okay, if you're still not convinced. So algebraically, what we will do now is, although we have already concluded that it's not a linear phase, let's still verify, reassure us even more. So we have already found the frequency response, capital H of omega, right? This real part plus the imaginary part, like this. So let's actually find its phase. Okay, check what's the expression for the phase. Okay, so now this is just to convince ourselves, okay, that yes, it's indeed not a linear phase system. So we had this, right, and plus j times 2 sine 7 omega minus 3, actually we had 2 sine 8 omega and minus 3 sine 7. Now the phase of this frequency response, which is given by tan inverse of the imaginary part divided by the real part. So what is it? 2 sine 8 omega minus 3 sine 7 omega divided by 3 cos 7 omega minus 2 cos 8 omega, right? And now you can clearly see that this phase is not a linear function of omega, right? It's not a linear phase. Clearly, you can't simplify this or convert it into some form which is a linear function of omega, right? You can't convert this to some alpha omega plus beta form. So for linear phase, we have the phase of the form alpha omega plus beta, right? So this is clearly, you can't actually equate this with the form of alpha times omega plus beta. It's clearly not a linear phase. So again, you are reassured that this is not a linear phase system. Okay, so we have looked at this part C in multiple directions, okay, just to convince ourselves that yes, our conclusion is correct. So yeah, so hopefully it was clear. So that's it. So question number 1 is done. Let's move to the next question. Let me check if the recording is okay. Right. So yeah, let's see question number 2. Okay, so assuming a linear phase FIR filter with real value coefficients and a 0 at 2 times e power j 0.5 pi, which of this is true? So we are given 4 options and we need to pick the right option. So we are given a linear phase FIR filter, okay, and we have a real valued impulse response, basically the coefficients of the filter, which is h of n. The impulse response has real valued samples, and capital H of z has a 0 at z equals to 2 times e power j 0.5 pi. This is all which is given, and now we need to check which of these options is true. So the first option says that there are another 3 zeros, there are 3 more zeros at 2 times e power minus j 0.5 pi, 0.5 e power j 0.5 pi, and 0.5 e power minus j 0.5 pi. Okay, so in option B it says there are more than 3 other zeros. Okay, and in C there is just another 0 at 2 times e power minus j 0.5 pi, and the last option says that all the zeros in the filter are within the unit circle. So if you recall your lecture notes, then the answer should be you should be able to answer this question in just 2 seconds. That's it. So this actually is based on the concept of the relationship between the zeros of a linear phase FIR filter. Okay, so if you recall that for a linear phase FIR filter, if let's say we have a 0 at some z equals to z naught, let's say, okay, and since we are dealing with real valued impulse response, see the real value coefficients. Okay, so for whenever h of n, small h of n, the impulse response whenever is real, we know that the poles and zeros of capital H of z are complex conjugates of each other. So if there is a 0 at z naught, then there will be another 0 at z naught star, which is the complex conjugate of z naught, right? That's fine. So clearly we have a 0 at 2 times e power j 0.5 pi. So we also have, due to this real valued impulse response, we also have another 0 at its conjugate, which is 2 times e power j minus 0.5 pi. Okay, so okay, we have already found another 0. That's fine. Okay, so and clearly you see, like the fourth option is definitely not true, because in the fourth option it says that all the zeros in the filter are within the unit circle. Even if in the question itself it's given that we have a 0 at 2 times e power j 0.5 pi. So this 0 is clearly located outside the unit circle, right? It is at a radius of 2 units from the center. So it's clearly outside the, and at an angle of this what's the angle? It's pi by 2, right? 0.5 pi means pi by 2. So yeah, but its radius is 2, so it's clearly outside the unit circle. Okay, so definitely there's a 0 outside the unit circle, so option D is clearly not possible. So just by mere observation you can eliminate some of the options in these kind of MCQs. Okay, so anyways, let's continue. So we saw that, okay, there's another 0 at its complex conjugate, okay, because of the real impulse response. So there's another 0 at 2 times e power minus j 0.5 pi. That's true. And now additionally because of linear phase, we saw, as we saw in the lectures, in the videos, that we also have another 0 at the inverse of z0 as well as the inverse of z0 star. Okay, so it's like reflected zeros about the unit circle. Okay, that's the thing. So these are all discussed. Okay, just in case you don't recall them, just go through the videos or the notes. So basically we will have total 4 zeros. Okay, so we are discussing question number 2. So far what I have dictated, let me write it here. If z0 is a 0, of a linear phase FIR filter, then the other zeros are, at first we have its complex conjugate, which is z0 star. Okay, that comes from the consequence of the real valued impulse response. Okay, and then we also have a 0 at z0 star inverse and another 0 at z0 inverse. Okay, so basically if z0 is of the form r times e power j theta, okay, you have your other zeros are the other zeros are z0 star. So what is z0 star? If z0 is r e to the power j theta, it's r e power minus j theta. That's the another 0. And then we have z0 star inverse is also a 0. So z0 star inverse would be 1 by r e power j theta, and finally z0 inverse would be 1 by r e power minus j theta. Correct? So altogether you have 4 zeros. Okay, so if one of the zeros is given, you can deduce the remaining 3 zeros. Okay, so if you visualize it, right, so let this be the unit circle. So this is the real part of z, this is the imaginary part of z. Okay, and so initially we started that if z0 is r e power j theta, if we have a 0 at r e power j theta. Okay, so let this be somewhere here. Okay, so this is r e power j theta, and here we are assuming that r is not equals to 1, it's not on the unit circle. Okay, and here we are considering that r is less than 1. You can also take it greater than 1, it's fine, but r is not equals to 1. So the thing is, if r were equal to 1 exactly, then all these other zeros you see, r times e power minus j theta, then 1 by r e power j theta, and all these things, they will also lie at the unit circle only. Okay, so yeah, so if you have this 0 at r e power j theta, the other 0, you have one of the other 0 at r e power minus j theta, which is its complex conjugate. Okay, so I'll use another color, so you'll have another 0 at here. So this is r e to the minus j theta. You will also have another 0 at 1 by r e power j theta. So 1 by r e power j theta. So the phase angle is theta, which is same as the first 0, which is drawn in the first quadrant. So it will have the same phase angle, but its amplitude is 1 by r. So since r here we have taken inside the unit circle, r is less than 1 here, so 1 by r would be greater than 1, right? And it will be exactly, this 0 will be exactly located at the reflection of the first 0 above the unit circle. So it's somewhere like here, right? So this is 1 by r e power j theta. It's the reflection of r e power j theta above the unit circle. And similarly, what about 1 by r e power minus j theta? It's simply somewhere here. So this is 1 by r e power minus. Fine. And this value is actually, so this is z equals to 1. This is z equals to minus 1. This is the unit circle basically. Okay, good. So that's fine. So these are the 4 zeros basically. So complex, and these are all complex zeros. So complex zeros, and remember we chose r not equals to 1, because in that case if r equals to 1 we would have the zeros to be lying on the unit circle. Here actually the reflection is distinctly visible because we are reflecting about the unit circle. So 1 0, if it's inside the unit circle, then the other one would be clearly outside the unit circle. So there would be no question of a 0 lying exactly on the unit circle. So that's why this is the case for r not equals to 1. So complex zeros having r not equals to 1 occur in sets of 4. So altogether there are 4 zeros, right? We just visualize them on the 4 0 plot. Fine, so far so good. So if you go back to the question, already you have 1 0 at 2 times e power j 0.5 pi. So you can easily find the location of the other 3 zeros, right? So you know from this concept that there will be 4 zeros. And if you go back to your options again, so option B again, you see there are more than 3 other zeros. So it says there are more than 3 zeros, more than 3 other zeros actually other than the given one. So that's not true, right? It's not true. So you can rule out option B as well. So like this you can follow the method of elimination just by observation. So but anyways, so now let me go to the next page. So we have already been given that we have 1 0 at z0 equals to 2 times e power j 0.55. This was given in the question, and now there will be 3 other zeros, right? First you take the complex conjugate of the given 0, then you take its inverse, and then you take the inverse of the given 0. That's it. So if there is a 0 at z equals to z0, there is another 0 at z equals to z0 star, there is another 0 at z equals to z0 star inverse, and finally the fourth 0 is at z equals to z0 inverse. So if you do that calculation, so you'll have we also have 1 0 at z0 star, which is this, and we have 1 0 again at z0 star inverse, which is this, and finally we have another 0 at z0 inverse, which is this. So these are the 4 zeros. The first 0 to e power j 0.55 was already given in the question. So we have 3 other zeros other than the given one at these locations: z0 star, z0 star inverse, and z0 inverse. So this is clearly your option number A. Okay, and option number C is definitely not true, because it says that this is just another 0 at this location, but we saw that actually there are 3 other zeros apart from the given one. So clearly option C is also wrong. So option A is the right answer. Okay, so answer is A. So hope this was clear. This is just a concept based on the relationship between these zeros of a linear phase FIR filter. So they occur in sets of 4. Okay, provided r not equals to 1. That's it. So that's it. Okay, so this is end of question number 2. Now going to question number 3. Okay, let me check if the recording is in progress. Okay, fine. This one. Okay, yeah. So question number 3. We are given 2 filters with real valued impulse responses, of course. So the first filter is given by, the impulse response of the first filter is given by h1 of n, which has 4 samples starting with a1 followed by a2, again a2, and finally a1. Okay, and the impulse response of the second filter is similarly given by h2 of n, which is b1 comma b2 comma b2 comma b1, and here these coefficients are not equal, that is ak is not equals to bk, so you don't have these coefficients matching with each other. So a1 is not equals to b1, a2 is not equals to b2, that's what it means. So they are clearly different coefficients for the two different filters. So now the statement given is that both these filters have the same phase response. We need to find whether it's true or false. Okay, so again this is a conceptual question. So if you were to actually solve it numerically, okay, if the concept is not known to you, what you could have done is you could have solved it numerically by first taking the DTFT and then finding its phase, okay, and then you would have checked whether the phases of these two filters are same or not, and then only you could have concluded that okay, they have the same phase response or they don't have the same phase response. So, and that turns out to be a tedious job actually, because you see it's a length 4 filter, both of them are length 4 filter, and once you take the DTFT there will be terms e power minus j omega, e power minus 2 j omega, e power minus 3 j omega, up to e power minus 3 j omega terms will be there, and then finding its phase, so that becomes numerically tedious, but we can avoid all those things if we just apply the concept that was discussed in the lectures. So if you recall your notes, it was mentioned that the phase response, which is actually given by minus alpha omega plus beta, okay, so because it's a linear phase, so minus alpha omega plus beta, the phases of this form, where alpha is the group delay basically, and it is equal to capital N minus 1 by 2, where capital N is the length of the filter. So this phase response, which is minus alpha omega plus beta, it was proven that it is only dependent on the length capital N, because what I was just now saying is that it's minus alpha omega plus beta, right, where alpha is actually equal to capital N minus 1 by 2, and beta is just a constant, it's either 0, pi or something. So overall it's just dependent on capital N. You see this phase response, just a second. Okay, yeah, so like I was saying, so this will be, the phase response will be dependent only on the length capital N, and it is independent of the impulse response, which is h of n. So we can actually have random coefficients in h of n, okay, they can be different, they can be random, as long as the length of the two sequences are same, and as long as we have symmetry we will actually get exactly the same phase response. That's a fact. So here also we are given two sequences, H1 of n and H2 of n, for the two different filters. All we need to check is that, first of all, if they are of the same length or not, and if they have symmetry or not. If yes, then that's it. We can easily conclude that both of them will have the exactly same phase response. Okay, so this way we will be avoiding that tedious calculation that I was talking. Okay, so let me just write it down. So far what I have told, I'm actually discussing these questions in a bit more detail, I guess. So for those who are pretty much familiar with these concepts, you can directly go ahead and skip these parts and just solve it yourself. For those who are listening it for the first time, if these concepts are new, then it might be useful for them. So anyway, so we are looking at the third question, and two filters with real valued. So mostly we are discussing these conceptual questions. You see, if you are familiar with the concept, then it's easy to solve. Otherwise, you might have to think for a while. So okay, responses, spelling was incorrect. So response, yeah. Okay, so first one was H1 of n equals A1, A2, A2, A1, and this arrow indicates that it corresponds to n equals to 0 index, and we had H2 of n equals, it's similar, instead of AI we had BI, and again this was the starting index. So, and remember, AK here is not equal to BK. So the important remark is that what I was saying, what I was dictating is that the phase response, which is this, where alpha is actually minus n minus 1 by 2. So it's basically the length in minus 1 divided by 2, and alpha is actually turns out to be the group delay of the filter. So this phase response is only dependent on the length capital N, and is independent of the impulse response. So what I was saying is that, so these sequences H1, H2 of n, these can have random coefficients, different coefficients, but as long as the lengths are equal for the two sequences, and as long as we have the symmetry, we can conclude that they have exactly the same phase. So we can have random coefficients in H of n, but as long as the length is same and we have symmetry, we will get exactly the same phase response. So if you go back to our given question, so h1 of n is the sequence starting with a1, then a2, and again a2, and finally a1. So if you plot it, it kind of looks like this. h1 of n, so let's say this, at n equals to 0 we have a1, this is a2, again a2, and then finally a1. This is n. And what about h2 of n? It's just the same thing except for the fact that you have b1 and b2 instead of a1 and b2, but this ai's and bi's, they are not equal. So a1 is not equals to b1 and a2 is not equals to b2. So for h2 of n, let's say we have something like this. Since the coefficients are different, let me take b1 like this. So this is b1 at n equals to 0. Again let me choose b2 to be something different. Okay, so let's say this is b2, and then we again have b2 at n equals to 2, and finally we have b1 again at n equals to 3. Fine. Okay. So clearly you see, if you observe both these sequences, first of all they have equal length, right? Its length equals to 4, capital N equals to 4. There are 4 non-zero samples, that's it. So from 0 to 3, small n equals to 0 to 3 we have, which means capital N equals to 4, the length is 4. Okay, so both of these filters have the same length, that's true. And regarding symmetry, if you observe that both of them have what kind of symmetry? Even symmetry, right? And it is actually about the point which is midway between the samples at n equals to 1 and 2. Okay, so it's like the symmetry is actually about this point. Oops. Yeah, so this is the point about which there is even symmetry, right? And similarly for this also. So between n equals to 1 and n equals to 2. So that's it. So we have seen that okay, coefficients can be different, can be random, but as long as the length is same and as long as we have symmetry, both these filters have exactly the same phase response, which is true in our case. So both these filters will have the same phase response. So we have seen that here just to put it in words, length, which is capital N, is 4. It's a 4 length sequence in both the cases, which is of course a even number. And symmetry, what kind of symmetry do they have? Both of them have even symmetry. So we have even symmetry and even length, and which implies that it's a type 2 filter, right? If you again go back to your lectures, for type 2 filters we had even symmetry as well as even length. So this is type 2 linear phase FIR filter. Okay, and since they have the same even symmetry and exactly same length, you can conclude that both have the exact same phase response. So that's it. So actually it was the statement that was given in the question, right? That they have both these filters have the same phase response, and we need to check if it's true or not. So it's actually indeed it's true. So the answer is actually true. So where should I write it? We run out of space here. Anyways, let me write it here only. So it's true. The answer is true. Okay. And this is the justification. Now, okay. So this was purely conceptual. So merely by looking at the symmetry and the length of the sequences, you can conclude it. The other approach which I was saying, like taking the DTFT, finding their phases, equating them, checking if they are equal or not, turns out to be a tedious process because it involves calculation for sure. But let's also verify this. Let's also so see, what I'm trying to explore is basically try out different approaches and then verify the answer if you still get the same thing or not. So let's try to verify this answer algebraically as well, okay, using the lengthy process. So let's do that. Okay, so let me go to the next page. This is okay. So in general, the frequency response is given by magnitude times e power j theta, right? And our theta of omega is basically, because of linear phase, we have the phase of the form minus alpha omega plus beta. The reason why we actually put minus sign in front of alpha is because once you take the derivative and you compute the group delay, which is actually the negative derivative of this phase, once you calculate the group delay for this phase equal to minus alpha omega plus beta, you actually get the group delay to be positive because it's the negative derivative. So since we want the group delay to be positive, that's why we actually put a minus sign in the phase response. So this is actually our phi of omega, the phase. Okay, and remember for both the sequences h1 of n and h2 of n, see they were length 4 sequences, right? N equals to 4, capital N was 4. So capital N equals to 4, and the group delay, which is alpha, is given by capital N minus 1 by 2 is the formula. So it's 3 by 2, and beta is usually 0 or pi basically. So both here the filters are type 2 filters, and while calculating the specifications for type 2 filters, we actually, not the specifications but the characteristics of the type 2 filter, while we actually checked for the non-trivial solution case of the linear phase for types 1 and type 2 filters, we put beta equals to 0 there, and it's also valid for beta equals to pi as well. Okay, but anyway, so if you do that, if let's say beta is 0, then you get this phi of omega to be it's minus alpha omega plus 0, so it's minus alpha omega, and alpha is 3 by 2, so minus 3 by 2. Okay, so that's fine. So actually, yeah, this is what will happen in this case. Actually, they have exactly the same phases. You can also put a plus pi or whatever. If you add a plus pi here, both of them, phi 1 of omega, phi 2 of omega, for the two filters will have exactly the same phase response, right? You can also put it 0, put beta equals to 0, that's fine, anything is fine. So anyways, now coming to the tedious approach. So we had, remember, small h1 of n, the impulse response, as a1, a2, a2, a1, right? So this a1, a2, a2, a1, this was given, right? So once you take the DTFT, what do you get? Oops, it's not A3, it's A1, because it's symmetrical, it's even symmetrical. Okay, so the first coefficient is exactly equal to the last coefficient, the second coefficient is exactly equal to the second last coefficient, and so on. So this is even symmetry, and so yeah, this is the expression for DTFT. Now So you can write this as one plus, I can take a1 common, this plus a2 times, or actually a2 times e power minus j omega, 1 plus e power minus j omega. Yes, we can write it like this. Now what I will do is, see this term here, the first term here, 1 plus e power minus 3j omega. Okay, so this is of the form 1 plus e power minus j omega whole cube, and 1 can also be written as 1 cube, so a cube plus b cube form, correct? And we know that a cube plus b cube is given by a plus b times a square, which is 1 square, minus ab, which is this, plus b square, which is e power minus 2j, right? So why I am actually using this a cube plus b cube formula, because that way if we expand it, we can actually factorize it, and we will have one factor as 1 plus e power minus j omega, and since we already have a factor of 1 plus e power minus j omega on the second term here, we can actually take that common. Okay, so that's why I'm writing it like this. So this is, you can write it as a1 1 plus e power minus j omega, 1 minus e power minus j omega plus e power minus 2j omega plus a2 e power minus j omega is. So now if I take this common, I have a1 minus yes, I think this is fine. Okay, so you see it's already a bit lengthy process, but anyways, let's see where we go. So this is this, and use the cos theta plus j sin theta formula. Okay, now I am actually writing it, I am actually putting the real parts together and the imaginary parts together. So what you will have is this. Okay, now what I will do is, see, there is a cos 2 omega term here, and also there is a sin 2 omega term, and what I will do is I will use the formula cos 2 omega equals to 2 cos square omega minus 1, and sin 2 omega, as you know, is 2 sin omega cos omega. I will use these two formulas, and then what you will get is so. Okay, so clearly this a1 gets cancelled with a1 here, and you can take cos omega common for the real part. Similarly, you can take j sin omega common for the imaginary part, and yes, you should get something like this. Okay, now you see these two factors here. So again, you can take this a1 2a1 cos omega and a2, this term here, you can just by adjusting a negative sign, you can take that common, so you will get 1 plus e power minus j omega. This is, you can just take it outside, and you have minus cos omega plus j sin omega. Okay, okay, so this is your h1 of omega, h1 of e power j omega, and similarly this is your h1 of, okay, similarly for h2 of e power j omega, everything will be the same. It's just that we will have b1 instead of a1 and b2 instead of a2. That's it. Rest everything is same. Right? Now if I divide these two frequency responses like this, so you see this 1 plus e power minus j omega term will cancel out. Similarly, the minus cos omega plus j sin omega term will cancel out. We will be only left with okay, this is what we have remaining. And you see these coefficients a1, a2, b1, b2, they are real valued, right? It's already given. These coefficients are real values. So this function here on the right hand side involves a1, a2, b1, b2 and cos omega. So overall it's a real valued quantity, right? It's a real value. So this is a real value. So if I take the phase on both sides, so the phase of h1 of e power j omega by h2 of e power j omega. Now what's the phase of this term on the right hand side? So the phase of any real value is 0, right? It has no imaginary part, so it's tan inverse 0, basically it's 0. Okay, so it's 0. And what is this phase of this ratio? Is simply the difference between the phase of the numerator and the denominator, right? So this is 0. Finally we can write that phase of h1 is equal to phase of h2. That's it. This is all what we needed to check. So see, they have exactly the same phases. Exact same phase response. So we have verified it algebraically as well. Okay. So but still this took a while. This was very much tedious. In exams you should not work out this way, rather it's simple concept based. So you just apply the concept and answer in no time. Okay, so that's it. So I think we solved question number 3 also. Now coming to question number 4. Okay, so let's see question number 4. Okay, but before that let me see if the recording is going. Fine. Alright. Okay, so yeah, in question number 4 you are given the transfer function of an FIR linear phase filter given by capital H of z equals to z to the power minus 2 minus z to the power minus 6. We need to determine the type of the filter. whether it's a type 1 filter or a type 2 filter or a type 3 or a type 4. Okay, so how do we do this? We know the characteristics of these individual types of filters, right? Based on symmetry and the length, we are able to categorize them into these 4 classes: type 1, type 2, type 3, type 4. Okay, so if you remember that table in the lectures, so when we had even symmetry and odd length, it was type 1. When we had even symmetry and even length, it was type 2. Similarly, when we had odd symmetry and odd length, it is type 3. And finally, when we have odd symmetry and even length, it is type 4 filter. Okay, so if we can somehow check the symmetry and the length of the impulse response, and then we can directly conclude whether it's a type 1 or type 2 or type 3 or type 4. Okay, so that's all we need to do here. I hope it's clear. It's pretty much straightforward. So I'll write it here. So we're looking at question number 4. Capital H of Z is given by z to the power minus 2 minus z to the power minus 6, and you know the general formula for Z transform, which is summation n running from minus infinity to infinity small h of n z to the power minus n. So you can clearly write down the impulse response h of n by looking at the Z transform expression. So it's an FIR filter, right? So only there would be 2 non-zero indices corresponding to n equals to 2 and n equals to 6. So the coefficient is 1. So this is, I am starting at n equals to 2. Okay, then I have for n equals to 3 0, n equals to 4 0, n equals to 5 again 0, and finally for n equals to 6 I again have a 1. Okay, so now if you just plot it, this is n equals to 2, n equals to 3 it is 0, and okay, I'm sorry, extremely sorry, this is minus 1, right? At n equals to 6 the coefficient is minus 1, we have a minus sign here, right? You see, this is a minus sign, so the coefficient at n equals to 6 would be minus 1. Okay, so anyways, okay, so this is minus 1 at n equals to 6. So then this is the rough sketch of h of n. Okay, so now the observation is that from this picture we can see that the length of the filter, which is capital N, is equal to how much? 2, 3, 4, 5, 6. So the index small n runs from 2 to 6. Okay, that's it. So from 2 to 6 there are 5 samples, right? The length of the sequence h of n in is 5. It's a 5 length sequence. So capital N is 5. There are 5 points. Okay, from small n equals to 2 to small n equals to 6. And of course this is odd. And what about the symmetry of h of n? It is clearly odd symmetric, right? And the point of symmetry is about n equals to 4. So this is the point of symmetry. Okay. So the symmetry is clearly odd, because you see at n equals to 2 we had the value of h of n as 1, and at n equals to 6 we have the exactly equal but opposite value, so it is equal to minus 1 at n equals to 6, right? So it's an odd function clearly, so it's odd symmetric. So symmetry is also odd, and this corresponds to which type? It is type 3, right? In type 3 we had both the length and symmetry as odd. Therefore this is a type 3. Linear phase FIR filter. So it's type 3. That's the answer. So out of these given options, type 3 is the answer. Third option. Okay. Now also if you further want to investigate, so h of z is given as z to the power minus 2 minus z to the power minus 6. If you actually visualize the poles and zeros, so this can be written as this. Okay, so if you observe the poles and zeros, so this is real part of z, this is imaginary part of z. You have a 0 here, you have a 0 here, you have a 0 here, and by the way this is the unit circle, so this is z equals to 1, this is z equals to minus 1, this is basically the point on the imaginary axis, z equals to j, and this is z equals to minus j. So these are the 0 locations, right? From this rational transfer function, you can write it. You can just plot the zeros. And similarly, we have 6 poles at the origin, 6 trivial poles. So what I will do is I will plot one pole and just write 6 here. So this 6 indicates the order of the pole. Okay, there are 6 trivial poles. Alright. So you see there are zeros at both z equals to 1 and z equals to minus 1. So capital H of 1 and capital H of minus 1 both are 0. And this is only true for the type 3 filter. If you revisit the lecture notes where we had drawn the pole 0 plots, the type 3 filter had zeros at both z equals to minus 1 and z equals to 1. And this is why actually type 3 filter can't be used to design both low pass filter as well as high pass filter. It is neither applicable for designing neither a low pass filter nor a high pass filter, because for a low pass filter we want at omega equals to 0, which is basically z equals to 1, we want for a low pass filter the frequency response to be equal to 1. But see, we have a 0 at z equals to 1, which corresponds to omega equals to 0. So therefore the frequency response for type 3 goes to 0. Similarly, for a high pass filter, we want the frequency response at omega equals to pi, which is z equals to minus 1, to be 1, because we are looking for high pass. So at omega equals to pi, we want the value to be 1. But the frequency response goes to 0 again at z equals to minus 1, because of this 0 located at z equals to minus 1. So this can't be used. Type 3 can't be used for both low pass as well as high pass. So, and clearly from this pole 0 plot, you have zeros at z equals to plus 1 and minus 1, which is only true for the type 3 filter. So therefore this is a type 3 filter. Okay, so this is just further investigation. Okay. So you had already solved it by looking at the symmetry and the length. Okay, you had already concluded that it's type 3, but it's just an additional pole 0 plot that we have drawn. Okay, so my plan was to explore one particular problem in all different directions. Okay, so that the concept gets clear. That's it. That's why I'm putting so much time on the individual problems. So that's it. So okay, question number 4 is done. Now coming to question number 5. Okay, so we have been given capital H of Z as the transfer function of a type 2 FIR filter. So type 2 FIR filter it is given, and the impulse response has a length capital N equals to 6. So it's an even length clearly, because of course for type 2 the condition is symmetry should be even, length should also be even. So length is clearly capital N equals to 6, it's even, and the symmetry should also be even. Okay, it is known that the filter has 0 at z equals to 0.5 e power j pi by 3. So 1 0 location is known, it is given. Now we need to find the expression for capital H of z. Okay, that's the thing. So okay, fine. So you see again we had discussed a similar example, I think in question number 2. If you go back to question number 2, see, you are given 1 0 and you had to come up with the other 3 0 locations. Okay, so we saw that reflection property, right, about the unit circle, and we have what are the locations of the 3 other zeros. Okay, so you can apply that concept here also. 1 0 location is present already at 0.5 e power j pi by 3. You can easily find the locations of the other zeros, right? Okay, now wait, and like I was saying, like only by observation you can actually eliminate some of the options in some of the MCQs. That turns out to be helpful, right? Without using pen and paper, if you are able to eliminate one option, half of the job is done. So you see, it's a type 2 filter given, and for type 2 filter we know that the symmetry is even, length is also even. So if the symmetry is even, okay, if you just look at the options given for h of z, h of z, it's a FIR filter, so it's a finite length sequence, and we will have a polynomial in z, right? Okay, so it's a length 6, so there are 6 coefficients. So we have coefficient for z to the power 0, then z to the power -1, so on up to z to the power -5. There are 6 coefficients altogether for a length 6 sequence. So you see, we know even symmetry should be present for type 2. So just by looking at these 4 options, we can check which of them have even symmetry. We need to only worry about them. If we can find that one of the options has not even symmetry, then we can simply eliminate it. So let's just do that. So in option 1, what kind of symmetry do we have? It is clearly, see, it's a not symmetry, because you see the first term here 1, it is, the coefficient is 1 at n equals to 0, and the last term here at n equals to 5, it is -1. So they are not same, it's just they're equal but opposite, like an odd function. Similarly, you see the second sample, it's -3.5, and the second last sample, it's 3.5. It's just the negative of that, so it's clearly an odd symmetric function. Similarly for 7.75 and -7.75. Okay, so option 1 is clearly not possible because it is not even symmetric, it is odd symmetry. Similarly, if we check for option B might be a possibility because it's even symmetric. You see, the coefficients are exactly similar, the first and last, the second and second last, and so on. And for option C again, it's odd symmetric, you see, so you can eliminate it. And option D is even symmetric, so it is another possibility. Yeah, so we have eliminated already half of the options. 2 options out of 4 we have eliminated. So the only possibilities is option B and option D, because only they have even symmetries. So see how just merely by observation we have successfully eliminated half of the options. So anyways, so yeah, so now let's apply the concept actually. So okay, I should go to next page. We are in question number 5. Okay, this is given as type 2 FIR filter, and length of the filter is given as capital N equals to 6. Okay, and if you go back to if you recall your notes, lecture notes, remember for type 2, in the pole 0 plot, we had a 0 at z equals to minus 1. There is guaranteed to be 1 0 at z equals to minus 1 for a type 2 FIR filter, and which is why it is not ideal for it can't be used for designing high pass filters. So the pole 0 plot for type 2 was like this. You had definitely 1 0 at z equals to minus 1. Okay, and a direct consequence of this is, so for a type 2 filter, we have a 0 at z equals to minus 1. In case you are not familiar with this concept, you can go and watch the recorded videos. Okay, everything has been taught in the lectures. So if we have a 0 at z equals to minus 1, which is the case, clearly a consequence of this fact is 1 plus z inverse is a factor of capital H of z. Yes or no? It's true, right? If z equals to minus 1 is a 0, then 1 plus z inverse is a factor of a capital H of z. Now we have been given that 1 0 is at, what was the location, let me go and check once again, is at z equals to 0.5 e power j pi by 3. Okay, this was given at z equals to 0.5 e power j pi by 3. Okay, so if there is a 0 at this location, then it implies that 1 minus 0.5 e power j pi by 3 times z inverse is also a factor of capital H of z, right? Just a second. Right? This will be a factor. And now, like we solved for the second question, you remember 1 0 location was given for linear phase FIR filter. If 1 0 location is given which does not lie at the unit circle, then we can determine the locations of the 3 other zeros as well. So remember, if z0 was a 0, then z0 star was another 0, then we had z0 star inverse as another 0, and finally z0 inverse as the another 0. So similarly we have other zeros. So another 0 would be z0 star, right? So it would be 0.5 e power minus j pi by 3. So, and this would imply that 1 minus 0.5 e power minus j pi by 3 times z inverse. Again, this is a factor of h of z. Okay, 1 0 at. Now we will look at z star inverse, right? So that is at z equals to 2 times e power j pi by 3. So the factor would be 1 minus 2 e power j pi by 3 z inverse is a factor of h of z. And finally another 0 would be present at z inverse, which is 2 times e power minus j pi by 3, and the factor would be this, right? Fine. So we have the factors. So 1 plus z inverse is one factor. Okay, this is one factor, this is another factor, this is another factor, this is another factor, and this is another factor. So altogether we have 5 factors. Okay, okay, so therefore we can write h of z as the product of these factors. So the first factor was 1 plus z inverse. Okay, second factor is 1 minus 0.5 e power j pi by 3 z inverse. Third factor is this. Fourth factor is 1 minus 2 e power j pi by 3 z inverse, and fifth factor is this. Okay, I think this is fine. Now if you just expand this, you will get 1 minus 1.5 z inverse plus 2.75 z to the power minus 2. So you see, up to, if you calculate up to this point, if you calculate the coefficients up to z to the power minus 2, you can automatically predict the coefficients for the subsequent terms as well, for z to the power minus 3, z to the power minus 4 and z to the power minus 5, because they will be even symmetric, right? So it will be exactly the same, right? So this is again 2.75, and then we have okay, so this is our answer. And from the given options, it is option number B, the second option. Okay, great. So hopefully that this was clear. Now going to the last three problems. So this is a numerical answer type question. You often are given these kind of questions in the assignments, so I thought of discussing one numerical answer type question here. So okay, so this given information pertains to questions 6 to 8. Alright, so the frequency response of the rational transfer function capital H of z can be expressed as capital A of omega times e power j phi of omega. So this is the form that was discussed in the lectures, right? Amplitude times e power j phase response, and where this amplitude capital A of omega is real value, okay, and it is also sometimes called as the zero phase response, okay, and this phase here phi of omega is a continuous phase response. So we have seen this in the lectures. If you recall the lectures, you will be able to match these words. And so yeah, so this is one form of expressing the frequency response. And here capital H of z is a type 1 linear phase low pass filter, and it has length capital N, which is equal to m plus 1. It's fine. And okay, the zero phase response, this amplitude part capital A of omega of this filter, it satisfies these constraints. So it is almost equal to 1, approximately equal to 1 whenever omega lies in the interval 0 to pi by 4, and it is equal to 0 when omega lies in the interval pi by 3 to pi. Okay, great. Now we have another filter capital G of z, which is defined as G of z equals to z to the power minus m by 2 minus capital H of z. Okay, this is how it is related to capital H of z. Okay, and now if the zero phase frequency response of capital G of z, this new filter, is denoted by this G subscript zp of omega, then we need to answer these following three questions. At first we need to find, in question number 6, we need to find the zero phase frequency response of G of z at 0, okay, at omega equals to 0. So let's see. So what we will do is, first we will find the general expression for the zero phase frequency response gzp of omega, and then we can substitute omega equals to 0, and whichever points we need to calculate, we can substitute and find the value. Okay, so the question is a bit lengthy, but it's really simple. Okay, so right. Alright, so yeah, we are in question number 6. So this particular representation of the frequency response is like this: a of omega times e power j phi of omega. Phi of omega is the continuous phase, and this is a real number, and this is given as type 1 linear phase low pass filter. So it's a, of course it's a FIR filter, it's a low pass filter, and so it's a type 1 which is used as a low pass filter. Now so we know that this is given, right? Capital N is equals to capital M plus 1. This was given right here, the length, and we know that the group delay which is given by alpha is nothing but capital N minus 1 by 2, which can also be written as capital M by 2. Fine. Okay. Now, so this phi of omega is the continuous phase response, and phi of omega is actually given by minus alpha omega plus beta, and for type 1 and 2 usually this beta is actually 0. Okay, so your phi of omega is minus alpha times omega, and alpha is m by 2, so minus m by 2 omega. Okay, so far so good. And this zero phase frequency response, this A of omega, it was defined as, it is 1 whenever omega is in this interval 0 to pi by 4, and it is approximately 0 when omega is within pi by 3 to pi. Okay, it's fine. Now going to the next page. Now comes the new filter, which is capital G of Z, and remember it was given by Z to the power minus m by 2 minus our original filter H of Z. Okay, so and so we can put Z equals to e power j omega, right? So G of this and this is basically H of this. Okay, And what is h of e power j omega? So you remember in the starting we wrote, yeah, this zero phase response a of omega times e power j continuous phase, this form. This is h of e power j omega, so we'll write it exactly like that. Okay, so this is a of omega times, now e power j phi of omega. What is phi of omega? Phi of omega, we derived that it is equal to minus m by 2 omega, right? We just substituted the values of n, alpha and so on. We found that phi is the continuous phase is minus m by 2 omega. So let's put that here. Right? So clearly this is of the form alright. Now in the question it was mentioned that the zero phase frequency response for g of z is gzp of omega. So this a of omega term, if you express in this form, this a of omega term for g of z is gzp of omega. So now you see this zero phase term here is basically 1 minus a of omega, right? This part, I'm talking about this part. So this is the zero phase response of g of z, and we have multiplied that with e power j, j times continuous phase. Okay, so this is actually our gzp of omega. Okay, so our gzp, zero phase frequency response for g of z, is 1 minus a of omega. Alright, and in question number 6 we need to find this gzp of 0 at omega equals to 0. So that's straightforward. This is z, it looks like a 2, so that's why I just increased its thickness. So anyway, so putting omega equals to 0, we have gzp of 0 equals to 1 minus a of 0. Now a of 0, you go back, what was a of 0? See a of omega was 1 when omega is between 0 to pi by 4. So definitely a of 0 would be 1. Okay, so this is 1 minus 1, which is 0. So gzp of 0 is actually 0. Okay, this is the answer to question number 6. Now in question number 7 we need to just do the same thing for omega equals to pi. G is P of pi. Okay, so G z p of pi is again 1 minus a of pi. So again, if you go back to the definition of a of omega, so a of omega is 0 whenever omega is within pi by 3 to pi. So clearly a of pi is 0. So this is 1 minus 0, which is 1. Okay. Pi. So GZP of pi is 1. So question number 7 is also done. Now finally question number 8. In question number 8 we have been asked that if capital N, if the length capital N is equal to 7, what is the group delay for capital G of Z? Okay, so you see this H of Z and G of Z both actually have same phase response, because for H of Z, H of e power j omega is equal to a of omega, which is a real value, times e power j phi of omega, the continuous phase, and phi of omega was minus m by 2 omega. Okay, so H of e power j omega was e of omega times e power j phi of omega, and phi of omega we calculated, it is this. And similarly G of e power j omega we obtained as 1 minus a of omega times e power minus j omega m by 2. Okay, so only this part, this coefficient part, this zero phase response part was different, and rest was same. And okay, and so a of omega was real, it's given in the question. Similarly, so 1 minus a of omega should also be real. Okay, so it's a real value times e power j times continuous phase. And if you observe both this expression for h of e power j omega and g of e power j omega, the phase, continuous phase, is same, equal for both, which is minus omega m by 2. Okay, so that is the observation to be made here. Now so the phases are equal. Phase of g of e power j omega is same as so if the phase is equal, then of course the group delay will also be equal. So the group delay for h of z is same as group delay for g of z. Okay, and what is the group delay of h of z? It was alpha, and alpha is n minus, given by n minus 1 by 2, the length minus 1 by 2. And in question number 8, the length, given value of length is capital N equals to 7. So if you put n equals to 7, you have 3. The answer. That's the group delay. Okay. Group delay for g of z if n equals to 7. Okay, actually I should write for. For is a more appropriate word instead of. Okay, it's in the question also it's given for, so I will stick to the exact same term. Okay, so that's it. The group delay is 3. So we have solved all the questions. I have, I think, spent enough time on individual questions, so that it's clearly understandable. Okay, so this brings us to the end of today's live session, and we'll meet again on next Monday 6 p.m. So thank you. I'll stop the recording.